So today we're going to try and introduce Einstein's equations, and then, well, you have a lot of me today. So we're also going to try and connect with the behavior or how to study plasma scenarios. Coming from the GR point of view, I'm going to be heavily relying on everything else you're going to learn from the other lectures as to how to treat those equations. We already said yesterday that because of the nice features of the structure of the equations, we can discuss primarily everything that is related to the evolution of Einstein's equations kind of on their own. And the techniques we'll use there will be translated, will be able to be promoted easily to add some sources that you treat in some other ways. So I'll make some comments about that as we go along. But today I want to, in the first class, in the first lecture, to tell you, bring you up to speed on the GR side of things. So chatting with many of you yesterday, I could tell there is quite a bit of variations in how much you have been exposed to these. So I'll try and give you kind of the main ingredients for you to be able to then pick up further resources. You can always ask me to try and fill in the details. But by and large, everything I'll tell you today will be enough, I think, to get you up to speed to then look at the paper. For instance, you can go check Charles' paper on harm and understand why he does some of the things he does. From the point of view of the subtleties that work in the general relativity context bring. So yesterday we introduced a few concepts. We talked about how given a space-time that in principle has no distinctions of time and space, we're going to introduce some way of making that intuition surfaced. And for that, we choose a particular foliation with a completely arbitrary label of time, and our only restriction was that these surfaces were space-like. This is one particular way of formulating Einstein's equations. It's funny that in the context of kind of astrophysics, pretty much most of applications follow this rule, but this is not the only one. There are reformulations of Einstein's equations that cast everything with respect to null hypersurfaces. And it's funny that in the applications in, say, fluid, in ADS, CFD, string theory, the prevalent formulation is not the ones we're going to be talking about. It's one based on null hypersurfaces. And if you ask anyone in that camp, what is the standard way of doing numerical relativity, they'll tell you this is not the one. While if you ask astrophysicists, they will give you exactly the opposite answer. And this is just to show that the flexibility of inherent in general relativity manifests itself in more than one way, and depending on which particular problem you're dealing with, you will be able to try and decide what might be the best option for you. But for the context of astrophysics and the context of making contact with a lot of work that has been done already on the astrophysical setting, this is the most natural way to connect all the efforts. I also mentioned yesterday that we're going to pick a particular signature where I put a minus in there for time. So the label time, the coordinate, the first coordinate I choose for time, will have associated to it a minus sign. So if you think of writing the metric in a flat space-time, so there is no curvature whatsoever here, you can write it this way: minus dt squared plus dx squared, dy squared, dz squared. This is your standard kind of Euclidean way of computing distances, and we add that minus sign to kind of represent the pseudo-Riemannian structure, which actually what it means to, in the simplest possible term, is that there is a structure of a cone, a null cone. Any vector that is inside this cone has norm that is negative. Any vector that is tangent to that cone has norm that is 0, and that's what we recognize as a null vector or a null trajectory. And any one that has purely spatial has norm that is positive. So this vector has positive norm. That one has 0 norm. And anything inside has less than 0 norm. So we distinguish these hypersurfaces as space-like if its normal is time-like. So if the normal to this hypersurface is inside that cone, strictly inside that cone, we're going to say that's a space-like hypersurface. Of course, you are familiar with spherical coordinates. This is how the metric reads in Cartesian coordinates. But if we were to choose spherical coordinates, this metric gets written this way. It's minus this t squared plus the r squared, maybe I'm using too quickly a notation, d theta squared plus sine squared theta d phi squared. So the first thing we notice here, this is a very simple observation, that at r equal to 0, our matrix ceases to be invertible. So you see that at r equal to 0, all this collapses. You have nothing. So often we're going to have to worry about this. In this case, it's just a manifestation of a bad choice of coordinates. The coordinates, spherical coordinates, have a singularity at the origin. So this is not a problem. It's just a feature of the coordinates that we chose. But in the context of having complete freedom of choosing coordinates, remember we endowed or we brought in two quantities, the lapse function and the shift vector. We're going to worry about what our choices are, because we might have a coordinate singularity, and that will mean that at some point we cannot keep talking about the description of the space-time that way, at least with that set of coordinates. And it has been from the very beginning a point of tension or a lot of discussion as to where you have problems where your matrix or matrix ceases to be invertible, where that's a true problem or a coordinate problem. And this is something one needs to decide. So I'll give you two examples just to fix ideas, and this is something you could use in the afternoon on some of these projects that I'm suggesting. So before we keep going in kind of in formalism, let me talk about the black hole, the Schwarzschild spacetime. In Schwarzschild coordinates. So these are coordinates, let me denote it as t, r, theta, and phi. Many of you would have seen this, but let me just try and make some connections. And I'm going to use that notation. D omega square stands for just sine squared theta, d phi squared plus d theta squared. So this is the standard Schwarzschild solution, the solution that describes the unique spherically symmetric asymptotically flat spacetime that describes a black hole. If you take the limit of r going to infinity, of course, this goes away, that goes away, and we're back to this solution. So this is what we meant by asymptotically flat. If you go sufficiently far, you recover the flat solution. Then you see that we have problems at two cases. If r equals 0 or r equal to m, we have divergences. So if r is equal to 2m, we have a 1 over 0 here, and that one goes to 0. And if r is equal to 0, then we're going to have an infinite here, and then 1 over infinite there. So this space-time described by this metric seems to have problems at r equals 0 and r equal to m. This is, as I said, there were lots of debate, and you'd be surprised that philosophers even today discuss some of these things. Of course, philosophers can discuss about anything for as long as they care. But so this is not a true singularity. This is just a coordinate singularity. But this is the true singularity. It's a singularity of the black hole, inside the black hole. So let's do one thing that will come handy, but let's try and make connections with the lapse and shift that we defined yesterday. So remember we said that the metric, so distances can be written in terms of the full metric. It can also be written in terms of the concepts we introduced yesterday in the following form. And just as a notation, if I ever have a label dxi, that doesn't mean it's the Cartesian xi. It's just the label of your coordinate along the I direction. So we could be talking easily about spherical coordinates, for instance. So now we can just stare at this expression and at that expression and say, what are the values of alpha and the different components here? So the first thing we notice is that based on this, that alpha is equal to 1 minus 2m over r square root. That's just a simple identification. Then here we see that we would have in the general expression components that multiply dx dt, but we have none here. Right? Any dx dt will have a beta associated to it, but because we have none there, then we know that beta I is equal to 0. And then from here we know that HRR is 1 over 1 minus 2m over r. And then all the r ones, I'm going to use I. If I and j, whatever labels, these are labels on the spatial part, they are 0 for if they are not exactly equal both to r. And the last important thing I want to look at is that, remember I said here, if a vector has 0 norm, it's a null vector, or the tangent to this cone has to have distance 0. So the distance along the cone is always 0. So let's look for how those trajectories would look like in this set of coordinates. So we would have to be solving an equation of the following form. So because of, for convenience, I'm going to try and use this equation to obtain what dt divided by dr is. Yes?
Where is the d omega squared part?
Oh, great. So imagine that now, so d omega squared tells us that when you multiply here, oh, no, you're right. I thought it was a mistake. I wanted for I. Sorry, this is what I wanted to say. H theta theta is equal to r squared, h phi phi is r squared, sin squared theta, and h ij for I different from j. Thank you.
I'm just curious, how do you know whether something's a coordinate singularity or a geometric singularity?
Great. That's a great question. And a priori, you don't know unless you do further calculations. So one kind of brute force way of understanding that is just try and do a coordinate transformation. I'll show you an example here and see if you can remove it. But a better thing is to compute curvature invariance. I'll tell you a little bit about this in just a bit. And then evaluate if the curvature invariance, the scalars that you can construct, have pathologies at the points where your original coordinate system would have said, oh, there might be a problem. So it turns out if you compute a particular curvature invariant here, you find out that indeed at r equal to 0, things blow up, but there is nothing, no memory whatsoever of the r equal to m. Oh, if we have a true singularity, we don't have a way of dealing with it in classical gravity. So classical gravity has that problem. A singularity is a singularity. There is interesting that, let me just make a parenthetical comment on that. So in the case of fluids, we can have shocks discontinuities. So these are gradients going to infinity, and there is this idea that you heard yesterday from Pascal, that at shocks we can find the weak solution and determine what is the unique solution past that shock. In contrast, in the type of equations generativity has, we can never have that solution unless you put it by hand. So from smooth initial data, you will never generate the shock. The only thing you can generate is a curvature singularity. It's a singularity. At that point, the theory breaks down. We don't have a theory that supersedes it. So everyone is, the whole field of quantum gravity is trying to do that.
So suppose you're trying
Good. We're going to talk about that a little bit, but let me just maybe anticipate that. So if we have a singularity, the singularity can be hidden inside of an horizon. So there is something called cosmic censorship. That's a conjecture by Penrose that says every singularity is always hidden from outside observers by a horizon, by a black hole. If that's the case, we're going to discuss two possible ways of dealing with it. One is to say if you go sufficiently far inside, you can cut your simulation there, because inside a black hole, whatever you're doing shouldn't be affecting what happens outside. The outside region is the only thing you have access to with respect to making any measurements, so it doesn't matter what you do inside. And there are other ways of dealing with this as well. So I'll mention a few things. But so there we don't deal with the singularity, we just kind of find a way to shove it under the rug in a way that is consistent with the problem you're trying to solve. There are other cases where you actually want to find out what happens with the spacetime very, very close to a singularity that is naked. It's a singularity that is not covered by a horizon, a singularity that would potentially have an effect on the whole rest of the spacetime. But the best you can do is get the solution, get the spacetime up to very close to that point, and from there on you cannot say anything else, because the theory has broken down. So if we solve from here for dTdr, then you're going to have the dTdr is plus minus so imagine that I do kind of a TR plot. So very, very far from the origin, this goes away, and we have plus minus 1. So plus minus 1 is just telling us that far here, the cones are precisely what we expect from a flat spacetime analogy. They're there, they're not tilted, they point up with respect to time, and so we just recover everything we could get here. But as we go closer and closer, well, eventually at r equal to m, we're going to have a problem. So things are going to diverge there. So r equal to m is sitting somewhere there, so let's say. And what happens with these cones is that they get thinner and thinner. And here they collapse into one. So trajectories, null rate trajectories here are just piling up this way. Those that are incoming, those with a 1 of the sign, and the r sign will have the same from the r side. And we have the same on the r side of r equal to 2m. So constant null rays will just pile up in front, and the ones that are going are doing the same. So that it just says that in those coordinates, everything piles up at the horizon, either from the inside or from the outside. If you're trying to solve for an accretion problem in these coordinates, you're going to see kind of matter flowing to the horizon and just piling up there, and time basically going still. The time doesn't progress anymore. That is an artifact of the particular coordinates we have chosen. So let me just give you another option to write the Schwarzschild solution. And this is just one of very many. But let's just rewrite this in a different type of coordinate. So these are ingoing, Eddington, Wittgenstein, and we're still staying in a spherically symmetric black hole. We're just introducing a new time, which is related to that time by a weird transformation of that form. If you do this coordinate transformation with this time on that set of coordinates, the metric now will read in the following way. So the first thing we notice here is that, yes, indeed, for r equal to m, this one goes to 0, but nothing is blowing up. This one is going to 0, but this one is not. So we have a TR component of the matrix. So if we were to represent this one in matrix form, we would have well, we would have that. So if this one goes to 0, we still have an invertible matrix, and I'll tell you why we care about an invertible matrix in a second. We still have these two off-diagonal terms that will ensure there is an inverse to this matrix. So nothing strange happens in r equal to m. Of course, everything goes to hell at r equals 0, but that we knew should happen. So we can do the same exercise. Let's try and get what alpha and beta are. Immediately, sorry. Yes. The t tilde, yes. Yeah. Yeah, at r equal infinity, we're fine. And these are just labels, and you can ask how much is proper time you traverse to go to very small values for, and you're going to say it's a finite time. So this is another kind of thing that one has to get used to, in that in general relativity, coordinates don't really mean much on themselves. Even someone was asking this interesting question, think about that line element again, and think that you're inside r equal to m. If we're inside r equal to m, the t coordinate now has a plus sign in front of it. The r coordinate now will have a negative connotation. So r ceases to be r. It's now a time coordinate, because it is the thing that an observer will carry inside the possible cone that it's going. So now r begins to measure time, and t begins to measure some space coordinates. So coordinates are just labels. So the first thing we notice in this metric, as opposed to that one, beyond the particular functional forms, is that we have now a TR component. So TR component means we have a non-zero shift. And remember what the non-zero shift is doing. It's just making sure that the relationship between the points, the labels I assign at a point, as I go forward to the future, I have to move it in a particular direction to find the same labels. So what this is saying is that as kind of a trajectory is going in, or as we look at the normal to the hypersurface, the labels that we assign to that point are not the same labels that we would have here. So if I go normal and land there, these points actually have smaller coordinates than these ones, because we have a shift that say these labels are the same as that label. We're going to see what the consequences are when we compare to that graph over there. But so let's just finish the identification. So if we look at the lapse is the square root of 1 minus 2m over r. So that came out the same as that one. When we look at the shift, well, we know that, let's say, beta r, if we look at the definition, should be h r beta r. We only have a tr component. We don't have t theta t phi, so we know that beta theta and beta phi are 0. So, sorry, this is, we know it's the following. 2m over r is HRR beta r. That comes from using the coordinates r theta phi, expanding that out, and then trying to find out what is a component that has TR. And of course, we're going to have one from the first term and one from the second term. We have H, T, so what H, RR here will give a DR, beta RDT from the first and last term, and an R1 from the second in the first term and first on the second. So we have, sorry, and this is 4. Yes? Okay, so let me just do that. Let me just do what we did say above. So let me expand that thing. So we already took care of the alpha part, right? So let me ignore that dt square. So if I expand that out, let me use the r theta phi coordinates. So I have hij dxi plus beta I dt. So this will have terms that are like so, hrr, and I need, now I put r and r here, so I should put r's all through. So this would pick a dr from here, and say if I do this one with that one, I have dr squared, hrr dr squared. Then I have hrr. Well, let me just do it this way, it's going to be simpler. Dr plus beta r dt square. Let me not work all the r ones, because with this it's going to be enough. So here I took the rr. So we have to flow through or go through all possible values of I and j, which are r, theta, and phi. So the first one I took rr. The second one I took r theta. So I'm going to have you put r here, then I have to put r and r there. That gives me the dr plus beta r dt. If I put the theta here, I have to put d theta, beta theta, right? But then I have an r1, which is the theta r, right? Because I have to have all possible values of I and j. So there is an r1 that is h theta r right? So let's expand this out. So this will give me hrr. The first term is dr squared, right? And there is no other term that will give me a dr squared. This is the only one that provides a dr squared for me. So when I compare to, let's say, this matrix, I know immediately that hrr is equal to 1 plus 2m over r. I made a mistake here, so let me just hold on this one for a second. So let me just go backwards. So then I have hrr dr squared. I'm going to have hrr beta r dt squared. So another term is hrr beta r dt squared. And then I have this one, and this is where I made a mistake. Sorry. I would have had also the minus alpha squared dt squared. So I'm now putting together with the same factors of the d's. So dt squared, I'm going to have dt squared from here, and we'll have an r dt squared from there. Sorry, minus alpha. And that has to be equal to minus 1 minus 2m over r. From here. So I'm just matching the coefficients that they have, dt squared, dt dr, etc., by expanding the matrix. You look very confused. So stop me if yeah, okay, sorry. I don't need it, because I'm matching, this is the RR component, this is the TT component. And now let me look at the TR component. I have, from here, the only one that give me a TR component is the square of this term. So this will be 2 HRR beta R has to be equal, that comes from here, has to be equal to whatever I see in the dt dr. and that's equal to 4 m over r. So now I have to kind of begin to work my way to solve for this. So this tells me HRR beta r is 2m over r. From here, I know what HRR is. So I can solve for beta r. So beta r is 2m over r divided by HRR, which is this one. So it means that beta r right? And finally, I need to come here to find for alpha. Because now I have HRR, I have beta r, I have the right-hand side, and I can solve for alpha. The other thing, just so as to compare with the previous case, that we can do is just solve for, let's say in this case, for the null trajectories. So again, I put a 0 here. I'm going to imagine that I'm taking null trajectories that go at theta equals constant, phi equal constant. That means d theta, d phi are 0. The same thing I did there, but I didn't mention that. So then we can ignore this part. And what we would be solving is something that goes like 0 is minus So just as we did before, there we were solving for dt dr. So I can divide by dr squared this expression. And I have that. And then I leave it as an exercise, but check that the solution, this is a quadratic equation for dt dr. And what you'll find out is that dt dr, dt tilde dr, has two solutions. One is -1, and the r one is something that goes like 1 plus 2m over r, or 1 minus 2m over r, or something of this form. So what we observe here is the following. Take r going to infinity. That means that the two solutions will go to -1 and 1. We go back to the flat space-time result. We go back to our cones. So far out, we have the standard cone. At r equal to m, this one diverges, but this one stays -1. So that says that the incoming part of the null cone never changes. It's always pointing at 45 degrees that way. So while this one does turn around, and right at r equal to m points strictly upwards because it's divergent. So this one, what it's telling us is this cone begins to deform a little bit. At this point, looks like so. So I have on this side -1, so I keep that one unchanged as I move it inwards. And the further I go in, the more deformation it is coming from here. So this is a representation of this solution that has no singularity at r equal to m, because we don't see any problem here. The matrix is invariable, everything is fine. We also, in these coordinates, see that we can communicate a particle from this side into the black hole, because there is no problem for kind of a particle that has to move inside the null cone always to traverse. Because I go from here, that's a perfectly defined trajectory. It's a time-like trajectory. It has to be within the line cone. It gets to that point and it keeps going. So in these coordinates, you can study accretion problems very nicely. And again, I'm gonna, not because he's here, but there is a nice, very thoroughly written paper by Charles, I think, and Jordan McKinney, where they actually study, for instance, the Blandford-Snide problem something he's going to talk about, and translate from the standard coordinates that have been presented in coordinates that look like so into coordinates that look like this, and lots of issues that before were unclear due to the coordinate singularity are equal to m becomes much more transparent. We contrast these to that case. So in that case, at r equal to m, so while this cone here was perfectly well defined, here our cone collapsed. So it just looked like that. So there's no way to have a trajectory naturally in these trajectories, in these coordinates, to go through. Of course, this looks very deceiving, and I can even guess that it's confusing. Remember, these time coordinates is not the same as that time coordinate. So it's just our foliations are changing. T equal constant in this coordinate is very different from the t equal constant in that coordinate. So if we were to picture our foliation there, let me just erase word here. What is going on from our foliation point of view is that if this is the black hole, this is the horizon, in one case we have a foliation that indeed looks like so. It's regular on that. As it crosses through the horizon, this would be in the incoming Newton Wittgenstein. This would be t tilde equal constant. While in Schwarzschild coordinates, it goes like that. This t equal constant in the r coordinates. So it is no wonder that the physics we'll interpret in one case or the other one is completely different. But it's just an artifact of the particular foliation we have chosen. So is this clear? So as part of the exercise, as a homework, I'm suggesting, do try and get the equations of motion for a simple wave equation, one-dimensional wave equation for a scalar field in both these coordinates, and see what sort of pathologies you might actually pick up because of the coordinates you have chosen. But we're going to discuss this later. So let me bring this one down, and then we're going to try and discuss things related to the formulations. So having kind of illustrated the difficult features of a bad choice of coordinate, I hope that kind of gives you an idea that as much as we can, we want to keep track of this coordinate freedom that we have. Because in numerical simulations, when we're studying a problem that you, of course, don't know the solution of, you're building the space-time as you go, a bad choice of coordinates will prevent you from going past some particular regime. And so we want to make that freedom as manifest as possible so that we can interact with that freedom of coordinates, which we don't know priori what might be best, to try and then be able to have a successful simulation of a particular problem. So all this kind of machinery that we were building geometrically yesterday, and we'll do some more now, is in many respects related to that. We want to make sure we keep contact with that as much as possible. So again, we're picturing this. We have a normal here. We have the lapse and the shift vector. And let me just say some things that I'm not sure how many of you are familiar with this, but let me just remind you if you are, if not, at least give you enough of a description to have you understand what is going on. So I mentioned that in the space-time where, say, this is our metric, derivatives of functions or vectors will be sensitive to what the metrics are. So as an example, as a simple example, if we are talking about, say, the Laplacian of a function in Cartesian coordinates, you will write it this way in Cartesian coordinates. But if you were using spherical coordinates, what is it? I'm going to forget. You have like dr of r, dr of phi, 1 over maybe r squared. And then you have here the Laplacian in spherical coordinates. So you end up picking new terms that are not there in the Cartesian case. And this is just a manifestation that your coordinates are curved. Your coordinates are not regular in your manifold or in the space where you're trying to take the Laplacian. Now, the coordinates, once you go to a case where the spacetime itself can be curved, even you could have laid down nice, smooth, regular Cartesian coordinates, but if your spacetime is curved, something is going to react. The derivatives will have to know about that. That means that if you have, let's say, usually you picture a derivative by taking the value of the function at a point, the value of the function is slightly at this slightly different point, and then bring the limit of the difference between the two of them values over the interval. But the function itself could be changing, the space-time curvature could be changing, and then taking a derivative will have to react. We'll have to know about the fact that you have variations because the function varies or the vector varies, but also because your space-time might be curved. So because of that, there is this one introduce a particular derivative, which is the covariant derivative. And there is a unique one that when acting on the metric gives you 0. So we're always going to be referring things with respect to that derivative. And with respect to standard coordinates, or the standard kind of derivatives, this obeys the following rule. Let's say it's related. We're going to let me introduce two things. So d dA would just simply be the derivative along the coordinate label xa. But we also need to introduce something else that knows about the curvature, and there's something called the Christoffel symbol. And in less than 3 lines, I already used 3 different notations for the same concept. So let me just, derivative. So here I'm using dx as a derivative. Here I use d dx, and here I use a comma. All those stand for the same. Sorry, at some point when you see how unwieldy things get, you actually get to be very fond of writing things in the shortest possible way. So this is the object that will know about 2 things. We'll know about the curvature, and we'll know about the coordinates. So if your coordinates are not nice, smooth, and kind of uniform like Cartesian, these guys will react. So in particular, you can ignore all the rules that you might have been taught before as to how to take derivatives, say, in spherical coordinates. If you forget all that, you write the metric in spherical coordinates, the flat space-time metric in spherical coordinates, and then you work with this Christoffel symbol, you can kind of rebuild everything you know, and then you can forget about those mnemonic rules. So let me tell you now the basic rules. So if you take, what you can find is the following properties hold. So if you have a scalar function, the covariant derivative of the scalar function is the same as the standard derivative. So scalar doesn't necessarily care about where the spacetime is curved or not, because there's no direction. So when I bring it back, if I have a particular curve, so if my spacetime is curved and I have a vector pointing that way, and here the vector is pointing that way, it need not be because the vector changed, but now it's pointing that way because there is a curvature. So, but the scalar doesn't have that problem. So this is true for the scalar, but for the vector, the following is true. So what you have to do, if I want to compute the derivative of a vector, I have to take the standard kind of variation or differentiation of the vector with respect to whatever coordinate labels I'm using, but then I have to add this piece. If I have something I call a covector, which is, let me give you the definition and explain what the covector is. The only difference is kind of a minus sign, and the contraction has to be different. So notice that we're using a notation where repeated indices have to be summed, and this is something we already use when we make the comparison between a metric and the components with respect to alpha, beta, and shift, alpha and shift. So this one, it says that if you want the covariant derivative component 1 of the vector VC component 1 would be D1 V1 plus gamma 1, 1, and it would be the sum from I equal 1 to 4 of I, B, I. So we'll involve all the other components. So the covector, given a vector VC, the covector is defined this way. So we lower the vector index with the metric this way. So again, the indices are repeated. We have to add over all possible components, and then this gives us each component of the covector. And analogously, we can construct the vector from a covector this way. So we add over C, and this one gives the values of each component of the vector. So the difference between a vector and a covector is a vector multiplying a covector gives you just a scalar. So this is a definition. I'm going to explain a little bit how we use it. You don't have to worry a lot about it unless you're interested. You can go and read a lot more of that, or you can ask me offline. But these are some of the things we're going to use. So I need this concept. The other thing that this covariant matrix gives us is a particular relation. Consider a loop. And what we want to do is take a vector pointing in any direction. And we want to do is take this vector, transport it along one side of the loop, and then up to that corner in one trajectory and another one. If the spacetime is curved, once we get here, there's going to be a deficit angle. There's going to be a variation between the vectors transporting one way or another. So the quantity that relates this fact is called the Riemann tensor, and it's defined in the following way. So this is our definition. These expressions get further complicated when we're taking second derivatives. I mean, I can give it to you, but this is just an illustration. The main concept is that this tensor that we introduce is this tensor that allows us to measure whether there is a difference in having transported the field the vector in one way or another one, which will have in its essence be measuring where there is curvature or where your coordinates are kind of funny. This is the Riemann tensor, and someone was asking, how do we know if a singularity is a true singularity or coordinate singularity? So out of the Riemann tensor, the problem is this is a tensor. If we make coordinate transformations, we're going to change the values of this object. But if you construct a scalar, something that doesn't have free indices, that is what is called an invariant. So you can construct this one, multiply by itself, all with the indexes down, and it is a particular scalar, which is called the Kretschmann scalar. And for Schwarzschild, this is equal to r to the 6th. Sorry, m squared r to the 6th. And this is what I was saying. If you look at this, it blows up at r equal to 0. And if you evaluate it, once you do this, it's independent of the coordinates you're chosen. If you evaluate this, okay, of course it blows up at r equal to 0, but it's perfectly regular at r equal to m. And remember yesterday, I mentioned this, out of this tensor, we can construct the Ricci scalar and the Ricci tensor, and out of that we construct the Einstein tensor. So Einstein tensor tells us something, how some particular components of this should change dynamically in the space-time. Okay, so I need to introduce a couple more things, and then I can begin talking about the equations. Remember, we introduced this matrix H, Ij, which is intrinsic metric to the hypersurface. When the indices down, this I and J just run on the spatial indices. But let me define more generally the following. Take GAB. Let me construct that quantity. It's something. So I took the full metric, I added NA and B. So this is a symmetric object. So if I flip A and B, I get the same answer. This one obviously is symmetric because it's the same object twice with the two indices. And let me imagine that I do the contraction of this with NB. So what will that give us? So this one with that. Remember, we defined there the contraction of a vector or how to raise or lower indices. So this is nothing but an A. Now I have this other term. So we notice that this one is contracting that one. So I have to add over all possible pairs so out of all possible values of B. So this will be NA times the sum phi equal 1 to 4 NB and B. Some, just as a aside about notation, some people label coordinates from 1 to 4, others from 0 to 3. It's a matter of choice. It's whether you're a C or a Fortran person, I guess. That's an old joke, because these kids all use Python, so I'm not sure what it is nowadays. Or does anyone use Julia? Oh, shoot. I thought I was going to look cool by knowing what Julia is. I don't know how to use it, though. So one thing that I didn't mention is that this n vector, so it's a vector that is normal to the hypersurface. Of course, there are many, many vectors that are normal to the hypersurface. So we can have, given a vector, twice that vector is also normal to the hypersurface. So to pick a unique one, we add two further conditions. We want this vector to be pointing in a particular direction, so forward with respect to our time label. And also we want it to be normalized, to have unit normal. That means that NA has to be equal to something proportional to 1. So it has to be positive, negative. What value do you think it should be? Is it equal to -1 or 1? Louder? Minus. Okay, yes, it has to be minus because it has to be time-like vector. Okay, so now when we do this, I get a -1. So this is 0. I give NA times -1. This tells us that this thing that I haven't told you yet what it is, this sum of the metric plus this combination, whenever it hits a vector that is orthogonal to the hypersurface, we're always going to get 0, no matter what. So this is so cool that we're going to give it its own entity. So let me define it as HAB. This one is nothing else but that one when we restrict to the hypersurface. So it's that. So it serves two purposes. One, it gives the metric intrinsic to the hypersurface, but also it is something called a projector. When we hit anything but that H, what we're doing at the end of the day is just bringing any vector to be tangent to the hypersurface, right? Because any vector component that might be along n gets to be 0 at the end. And that allows us to define another relation. So this is a bona fide metric for that hypersurface. So that means that there is a unique derivative, just like the one we defined before, like that one, we call di, which is such that if you take this one is equal to 0. So far, we're doing nothing different from what we said before, except that now we're at the one lower dimension. And every relation that I wrote there also applies to this one, except that, for instance, if I'm taking the derivative of a vector Sj, I will write it as this form. And just to be perhaps overly careful, I put a 3 there. Sorry, let me just call it I. I put a 3 there to remind me that this is the Christoffel symbol associated to that metric. And of course, that one satisfies the same relation. If I have ijk, this would be h, k, l, h, I, l, comma j. So it's exactly the same. But we remember that there is a relation between the full metric and these things that we're inducing on these hypersurfaces. So there's a further relation between this matrix and that, this derivative and that derivative, whenever we're talking about vectors that only live on the hypersurface. So again, this is going to be rather technical. I don't expect you to fully absorb now. Ask me if you have questions, but we need to introduce this further concept. We're going to define the derivative of, let's say again, the relationship of the derivative, in this case for a vector, with respect to the R1, if I do the following. Yes. Let's say, suppose we define a vector Sj to be the projection of a vector that lives in the 4 dimension. So we have a full vector, and we only care about its projection on a given hypersurface. So I can define it this way. We can find that the derivative intrinsic to the hypersurface, acting on that vector that is now intrinsic to the hypersurface, is related to the derivative of the full vector with respect to the full derivative operator projected. So, and relations like these can be easily obtained for all possible tensors we care about. So why do we bother about this? It's because now we can begin to rewrite Einstein's equations in this geometric dynamics way. Any questions? Seriously, I don't expect you to be absorbing all this, so make sure you ask questions. It's a lot to be throwing at you, but we need to get you up to here so that you understand what else is going on. Uh, in a sense, well, it is obvious. You can take these metrics, this way, multiply by dx, db, then expand it, and then you see what really happens is that if you want, let me give you another relation, which I was going to give you in a second, but NA, let's consider this guy. Remember, NA was this unit vector pointing to the future, and now I said it has to be in unit normal, right? So now think of writing the full metric with respect to the alpha and the shift and this composition we had. So it turns out that if you take the original metric, written the way we had in terms of the kind of indices down, in terms of alpha, beta, and h. Now, compute is inverse. I swear that the following is true. What sits in the TT component is -1 over alpha squared. And then you have other expressions here, but so here we're going to have beta I over alpha, beta j over alpha, and this will be hij minus beta I, beta j over alpha square. So now, but the only thing we care about is this one. So this had to be unit normal. So we can write it, and remember this was grad of t. That's how we do it. It has to be proportional to the grad of t. It's the normal to that hypersurface. The hypersurface was defined by t equal constant. So the grad of a constant gives you, so the gradient is the orthogonal vector to that hypersurface. So in this means that NA is proportional, and let me just use proportional to ddta. But we need to find out what the proportionality constant is, or the proportionality function is. And by looking at this one, you can see that it's alpha. Right? Because if I take this vector, multiply, take the normal, raise its indices, and then multiply with itself, this will give me the -1. Okay, so that gives me the alpha. Now compute out of this one, using this, the TT component, the TI component, you're going to see that all of those give you 0. So H, T, whatever is 0. And so that's how you, and then Hij evaluated this way, it's the same Hij as we define. So once we do that, the R relation you can find is that NA, now we need index up, is 1 over alpha ddt A plus beta I dxi. So the vector NA, if you want, can be written as 1 over alpha, 1 minus beta. That comes from defining this way, computing the inverse and raising the index and seeing what it is. This is a particularly interesting combination because soon what we're going to try and find out is that many of the derivatives, many of the evolution equations of Einstein's equations will actually have like things of this form, NA grad A of something. These will have a ddt associated to it and something on space. And these are how the derivatives are going to come. So let me just go directly through it. In particular, we define KAB as grad A and B, remember yesterday. But we also want this K to be fully intrinsic to the hypersurface, so I'm going to project it. So I'm going to have H, I'll change this one to remember that we're contracting. So we take this grad, we fully project to the hypersurface, that's extrinsic curvature. We can now, armed with everything we have, so using this N defined this way, knowing how the derivative operator acts, having constructed the H, we can expand what this is. And what you'll get is the following. So here we just expanded that expression. This is our definition. This comes out straight from the definition. And it says the rate of change of our metric from one hypersurface to the next one is modulated by the extrinsic curvature, how this surface was embedded in the higher spacetime. And then it has a set of other things. That the moment we see beta, we already know that it's heavily influenced by our coordinate choice. So as remember I said, we want to keep track of our coordinate freedom as much as we can. And this is just making, every time we see something dependent directly on beta, such that if we set beta to 0, it's gone. This tells us it's just 100% related to our choice of coordinates. So this thing comes from there, and of course this guy also comes from it. Yes? Alpha and beta are indices, but we're contracting, so we have to run over all alpha. Yes? Say again?
Could you use something else as alpha and beta?
Yes, CD, CD. So as long as you're summing, yeah, you could, yeah. Sorry, I throw that in just because I usually when I have this contraction to keep track of what I need, I use the Greek letter that is associated to it. As far as I can push my Greek letters are like 4 or 5. So of course this, if we were doing it, for instance, in Schwarzschild coordinates, this would not be here because the betas were 0. Of course, alpha better be non-zero because alpha would measure the time that it takes, the proper time from one slice to the other one. If we set alpha equal to 0, we're just staying at that hypersurface. We're not moving from it, so nothing will change. So this is just kinematics. This is a definition. We now need something else that tells us how this guy is going to vary. If we can find out, now we will be in business. And this is what I'm going to tell you now. So remember we had Einstein's equations again. Equal something, but for the sake of the argument here, I'm going to put a 0. And again, I stress that we said that it didn't matter where we put a 0 or not, because it will be just lower order terms. For all intents and purposes, we're going to pick up sources, but that's all we're going to do if we consider something non-zero. So now remember we had this thing that was a projector on the hypersurface. We also have that thing, n. And then if we contract anything with n, we're saying pick of that thing, the component is along n, right? So if I have a vector, let's call it VA, and then hit it with NA, it would either give me the V parallel, the component of V parallel to n if there is something, or it will give me 0 if it is orthogonal to n. So this is just a projector, right? So we have a way to project along n, and we have a way to project orthogonal to n. So now I'm going to tell you something, and let's see. So if we take this equation and we hit it with NA and B, so we have two free indices. When we're hitting with NA and NB, what we're saying is that take this equation and just give me the component of it that is fully along n, right? So if you do that, you're going to get something, and I'll tell you how, but let me just give you the punchline, and you're going to get something that is known as the so-called Hamiltonian constraint. I'll just give you the expression so that we can connect with some things. I'm going to put here between quotes means that's because we're considering vacuum. If not, we're going to have a source. Yes? Exactly. Thank you. These three, remember, is like, where did I put that? The other 3. Somewhere here, there was a 3. It was saying you compute the Ricci scalar associated to H, not associated to G. Right? So we're trying to make sure we have, at the end of the day, an expression that tells us about what is going on at that hypersurface, and away from it with respect to geometrical quantities and making very manifest the coordinate freedom that we have. So this is, so Okay, good. No, that's an excellent question. So imagine that we have a 4D spacetime. So d equal 4. And in that d equal 4, we're choosing slices, which are one dimension lower. So this is d equal 3. But your question is excellent. In fact, there are ways, and there are ways to keep going. So we can take here. So we choose a foliation in this d equal 4. Now imagine that let me take this one and do this, right? So now I have this d equal 3, and it's pointing to you like that. Now you could say, I'm going to introduce another foliation. How you're going to introduce it will depend on your choice, but one very convenient one is for some particular problems, like they're like spherical ones. So this is d equal 2. And it can do everything we've said before, we can do again. So we can define a normal here, right? And then try to interpret the evolution of the intrinsic metric to that kind of ball that I have defined here, how it varies from one ball to the next one. And then you can do that, and then all these relations go through, except that we would have 3 to 2, 4 to 3, etc. But yeah, that was a pretty good question. So this is the Hamiltonian constraint. It would be a source. Now, suppose for the sake of the argument, again, I'm jumping up and down, but hopefully I'm trying to make contact with things that you already know. So we said this is purely coordinate choices. So imagine that it's 0. Now we have dt of h is equal to k. We're going to discuss the initial value problem in a second, but you could imagine that that slice we're choosing at some given moment is a moment of time symmetry. So the h is not really varying at that point. That means that k is 0. That doesn't mean that h is 0, but that means that k is 0. So we could have a case where k is 0. So neither of these two would be here, right? Because it's k squared, that's the trace of k. So this is equal to hij kij. This is a contraction of k completely with the intrinsic metric. So that will be 0 because this one is 0, and these terms would be individually 0. So you have this one equal to 0. What you can, with a few extra assumptions as to what the shape of h is, this is related to Laplacian of phi equal 4 pi rho. So you get the gravitational potential comes directly out of this equation in the right coordinates. And this potential comes out if you assume that hij is some potential, some phi to some power for technical reasons, multiplying the flat metric. So with this choice, this equation hides in it the standard Newtonian equation for the gravitational field potential. Now I can do NH with HBC, right? When I contract in this here, I end up with, I have to sum over A and I have to sum over B, so I end up with no free index, and that's what we can see here. There's no free index. If I contract with NA, I kill the freedom on that index, but I'm contracting with HB, which contracts over B, but I have a free C. So this will give me a free index that is spatial. So this was a Hamiltonian constraint. This is going to be the momentum constraint. This is, let me just write it a little bit. Which index did I leave? No, okay, C. So this gives you the derivative intrinsic to the hypersurface, acting on the extrinsic metric of the hypersurface, minus the derivative of the trace, equal to 0 in vacuum. Otherwise, you have a component there that is the mass current of your system. So this hides in it conservation of momentum. And the last one is if we contract with, say, HAC, HBD. If I contract this one with this, now I get a horrible mess, but it's the meat of everything. Where did I put the blackboard? So this will give us the following. Oh, let me just do this. Do I want to build? Let me just define CCA. Well, no, let me do this. Oh, shit. CD. Okay, so that's the last one. And it's the first one where we see the time derivative of k. So this tells us now how that extrinsic curvature of that slice changes upon us comparing from one slice to the next one. So the rate of change of that, well, let me just say for simplicity, so this is related to the corner freedom in this relabeling of points at a given hypersurface between one hypersurface and the next one. So let's imagine for a time being that this is 0. Here you have one where the derivative is with respect to alpha. That's just a corner freedom, and let's say locally take it equal to 1. So that, imagine that's gone from that. So we have the time derivative of k is equal to the following. So we have the 3r, and then things that depend on the extrinsic curvature and traces of. This again is the Ricci's tensor computed from the H metric. And so let me just make a few observations. So for the sake of the argument, let's imagine that we take alpha equal to 1, beta equal to 0. So the first equation tells us dt of h, and I'm going to ignore indices because of they don't matter for what I'm going to say now. It's roughly k. dt of k is roughly what? Will be r3 plus k squared, etc. So we know that the 3 of r, that one, remember by definition, where did we put them? This r comes from the Riemann tensor. The Riemann tensor has second derivatives of the metric. And then these are just traces, etc. So we have it here, we have second derivatives of h. So if I combine these two equations, I take the time derivative of this one, gives me the time derivative of k. The time derivative of k gives me this one. So what we seem to get is structurally, at least, second derivative of t of h, second derivative space of h, class what? Lower order terms. And if we have the right properties here in the principal part, we can ignore these ones, right? So this is almost there. We're almost in as good as a position as we can, except that I'm going to use a bad word. This freaking thing has more than one thing that can bug us. So let me just tell you, in general, how we could write this and the price to pay for having written this way, and maybe motivate what we're going to do with it. Let me just make sure I find it. Here. So let's imagine that we're any dimension, and we ask, how is the R of any dimensions? This is true for whatever. So let's suppose that we're in a D dimensions, and our metric is given by G. So if we're in 3 dimensions, this would be H, but the expression I'm going to write is general. This RAB is given by the following. So if we go through the Riemann definition, we compute the trace of it to just leave only 2 indices, we can write the Ricci tensor this way. And let's just try and recognize a few things. Again, for computing this guy, we would have put H's all through. So let's see what we have. So notice this piece. This says take the metric and contract over C and D the GAB. So if we were in the spatial, in this case, this would have been H. So we only have spatial derivatives. Let's imagine further, at least locally, we take a coordinate system such that the metric looks flat there. And we can always do this unless we're sitting on top of a singularity. So this will give us, and furthermore, let me just use that freedom to say I'm going to use Cartesian coordinates. So this will have second derivative of x GAB plus second derivative of y GAB plus second derivative of z GAB. Well, let's say in the particular case of the metric, so this is roughly what this term is giving us. From this argument, we would be having second derivative of t Hij equal this. So if this is all we had, this would be beautiful, Trump beautiful, very beautiful. This would be just a wave equation for each component of Hij. Each equation would have 2 speeds of propagation, plus and minus 1, and it is as good as it gets. Now let's keep going. So we know that this would satisfy all the hyperbolic things we could ask. In fact, it's the most symmetric hyperbolic form that we could have. So we said that if we were in that situation, we could throw away all the lower order terms. So let's keep looking at what else we have. So see here, and sorry to introduce another notation, this parenthesis, if you've never seen it, just means take this plus the exchange of this with A and divide by a half. So, but it doesn't matter because we're going to ignore it. The point here is that this is a metric derived once. So it's just one derivative, while here has 2 derivatives. So if everything goes well, we can ignore this piece. It's a lower order term. Then I come in here and have the Christoffels. The Christoffels, remember our definition, has only first derivatives. Okay, yes, they are first derivative square, but as far as the number of derivatives is concerned, we just have 1. And now I come to this one, and this is the annoying part. This is the place where everything dies. Here I have the first derivatives, but I'm having another derivative because of this one. So this has second derivatives. And it is when you consider this with that the system becomes weakly hyperbolic. And now we have one of two options. We either bite the bullet, say, well, our system is weakly hyperbolic. Weakly hyperbolic doesn't mean the problem will be ill-posed. It just gives us lots of red flags. It's only in a case-by-case basis that you can check whether it works or not. The other one is to try and think very hard as to what we can do with this term. And we can do several things. And this is what the new formulations of general relativity that are used in numerical simulations do. They either handle these by special coordinate choices or by introducing new evolution equations with this, with further constraints that one has to satisfy. And we'll discuss the general properties of those so that you understand what's going on. But speaking of constraints, let me remind you of a system you know very well, because we haven't talked about them so far. They don't show up in fluid dynamics unless you introduce magnetized fluids. But let me just remind you of Maxwell's equations in the last few minutes we have in this lecture. So you have and I could imagine that we're in the source-free case. We're only thinking about electromagnetic waves. So let me just put a 0 here. Or if you want, we can throw in some charge density. It doesn't matter. So notice a different structure. I'm just going to say things that you already know, but I want to then connect with that. So we have evolution equations. So if someone hands you a solution of an electrodynamics problem, what would that solution be? Well, someone will be telling you what the electric and magnetic fields are for all at any position and any time. So it would be the collection of E and B, so for all X and T. That makes sense. So you're saying, well, if I want to study this numerically, what will I do? And this is something that perhaps Charles will talk a little bit. So you're going to give the state of the field at some E and some time. And then you're going to evolve it to the future. Consistent initial data will have to satisfy these equations. These are just purely spatial. Here you don't see a time derivative, while here you do. But you're faced with the following problem. How are you going to get, or following feature, how are you going to get, so if you start here, so we all would agree that in order to study the evolution, you have to give initial data that satisfy these constraints here. How are you going to get to here? So one option is to take the E's and B's that you gave there, consistent with the constraint, i.e. they satisfy this constraint, and evolve to the future using this rule. This is a well-defined recipe. You just have, this one tells you how this E and B that you give initially, the rate of change of them as you go forward. But that's a choice. You could choose to evolve, let's say for the sake of the argument, 2 of these 2 equations, and add to that these ones. So you can imagine solving for EX, or let's say BX and BY out of this one. Why would you do that? I don't know, but let's say you could do that. BX or BY out of this equation. And out of that one, you could solve for BZ. So in the first one, you're only using the evolution equations. This, in the numerical relativity parlance, I'm not sure if they use it in astrophysics, we would call it a free evolution. It's an evolution that doesn't pay attention to the constraints. The other one would be the constrained evolution, which is one that or partially constrained, where it uses the constraints as part of the recipe to go forward in the future, to the future. The very same issue, or the very same feature, is present here. I have constraints. So these are equations very much like these two in that they only involve derivatives at every given hypersurface. So these are true at every given hypersurface. It constrains the degree, the freedom that we would have to choose freely the metric A, the intrinsic metric H, and the extrinsic curvature K. With that, consistent initial data has to satisfy these two set of this one equation and four equations. And then you would evolve to the future, but you could choose to use some of these as part of your evolutionary process. In fact, if you are in spherical symmetry, as we'll discuss later, the system is so-called fully constrained. You can forget about the evolution equations and then just only use these ones, just because you only have two things to solve for. But that's a choice. And it depends on your particular application, what may be more convenient for you. In the full 3D problem where everything is dynamic and there is no particular symmetry that you can take for to help you out, usually we're gonna just solve a free evolution problem. But because of this problem, we're gonna bring the constraints one way or another to our advantage. In this, sorry, singularities? Okay, so if you know your problem has symmetries to begin with, then you can impose those symmetries, right? You're gonna say there is, sorry, in the parlance of general relativity, there are some killing fields, and then you can use them explicitly. And the way they're gonna come in is they're gonna significantly restrict, where do you put that? The shape of the metric, let's say, I'm gonna use this one here. It's gonna restrict the kind of things you have here. So if you have purely spherically symmetric spacetime, you expect anything that has a theta component or a phi component to be decoupled from the rest. So rather than having this structure, you're gonna have something in the TR sector, and then the theta phi sector is something very simple. At most, you're gonna allow for, let's say, dilations of your spheres, but you want to enforce that as you go around the sphere, you don't see any change. So all those things you can build in from the get-go by imposing symmetries. That's perfectly fine. So you're gonna choose coordinates that are consistent with that. So for instance, in the problems that we could discuss later today, which are spherically symmetric, we're gonna use that very explicitly, where you're not gonna allow any dynamics on the theta phi. At most, what you would allow is that the r coordinates can change as a sphere at r equal constant might have an area 4 pi r squared, or might have an area 4 pi r squared times some function that will be time dependent depending on what is going on in the dynamics of your spacetime. But yeah, those you could do. But the issue of how to choose convenient coordinates, it's a problem in and of itself. There are convenient coordinates for kind of analytical studies. This need not be the best necessarily for numerical studies. But again, all these things tie non-trivially to the structure of the equations you want and the particular simplifications you like to see your code to exploit. So let's take a break, and then we start, I think, in half an hour. Thank you.